for the basic question, it gives us data and it says here are estimates of the daily intakes of calcium in milligrams for 38 women between the ages of 18 and 24 years who participated in a study of women's bone health. So part A asks to display the data using a histogram. Describe the distribution of calcium intakes for these women. So I put it in a histogram. Here it is on the calculator. Here it is on paper. This is kind of not good. So I'll show you this one. So I basically just plugged all the data that it gave me into list one and voila. And so obviously this is very skewed, right? Because the outliers are towards here that pull the data this way. So since it's skewed, to find the center, we would use the median and not the mean. So just describing the distribution, the range starts from 374 milligrams and it goes to 2,433 milligrams. I calculated the center in my calculator and I got 245 milligrams. And the potential outliers would be 1,933 and 2,433. Okay, so for part B, it says to calculate the mean, the standard deviation, and the standard error. So I just went in my calculator. I hit stat, calc 1var stat list 1, enter. And so with this, I get my mean is 926.0263. My standard deviation is 427.2295 milligrams. And my standard error, which for the formula, it is standard deviation over square root of n, which would be 427 divided by the square root of 38, which gives you 69.27 milligrams. Okay, so for part C, it wanted us to find a 95% confidence interval for the mean. And so I used all of the information previously found in part B, such as the mean and the standard deviation. So to solve this, you would use the equation, the mean plus or minus t star times standard deviation over the square root of n, and you'd use t star since we are not given a population standard deviation but rather a sample. So at the 95% interval, our t star would usually be 1.960, but since our degrees of freedom is 37, we would go in our table and go to 37 on the left, and then the 95% confidence interval at the bottom and meet in the middle, and you get 2.042. So just some assumptions, we would assume an SRS, independence, and although it is skewed because of part A, because of the central limit theorem, that n has to be greater than or equal to 30. Since n is 38, we do proceed. So I used this equation, and I found this confidence interval. So we are 95% confident that the actual daily intakes of calcium for women between ages of 18 to 24 years is 784.55 milligrams to 1,067.45 milligrams. Okay, so now for part D, it asked us to remove the two largest values and then compute the 95% confidence interval again, and it asked us what did we notice. So the two largest values were these two, and I just went to my calculator and went into the list one and then deleted those two values and then recomputed all of this. So I found that the mean was 856.1944 and that the standard deviation was 306.7296. So now our n value, which is the number of observations, is 36 instead of 38. So you have to redo degrees of freedom, which turns out to be 35, but then you have to round that down to 30 in the chart, and it turns out to be the same t star. So I did my confidence interval, and I got the confidence interval of 751.804 to 960.5 0.5847. So we are now 95% confident that the actual daily calcium intake for women 18 to 24 is between 751.804 and 960.5847. So the difference is that the interval itself, the numbers between these intervals got smaller, as well as the number themselves, and this is what happens when we remove outliers. Okay, now it's time for the advanced question, which says you play 2 games against the same opponent. The probability you win the first game is 0.4. If you win the first game, the probability you also win the second is 0.2. If you lose the first game, the probability that you win the second is 0.3. Okay, so for part A, it asks, are the 2 games independent? Explain. So I said, no, the games are not independent, since the probability of winning the second is affected by whether you win the first game. And the definition of independent is that the 2 do not affect one another. So that proves that they are not. Okay, so for part B, it asks what's the probability that you lose both games, and then for part C it asks what is the probability you win both games. So for this I decided to draw a tree diagram which shows the first game and the second game. So if you win the first and you win the second, and if you win the first or lose the second, and same all. So like lose first, lose second, lose first, win second. So that just is an easy way to map it out. And so then for B, the probability that you win both would be 0.6 times 0.7, which is 0.42. And then for part C, the probability that you win both is 0.4 times 0.2, which is 0.08. Okay, now, so for part D, it says let random variable x be the number of games you win. Construct a probability model for x. So basically what this is asking is, you've probably seen this in the textbook, so random variable x. So I could win 0, 1, or 2 games, and the probability of x, and here it is. So to construct these, I used the tree diagram that I made in the last problem. So for 0, which would mean that you lose both, it would be 0.6 times 0.7, which is 0.42. And then the probability that you win one game could either be you win and then lose, or you lose and then win. So our sample space could be WL and LW. So then I did 0.4 times 0.8, which is 0.32, or 0.6 times 0.3, which is 0.18. And so for 2, that can only be one thing. You win both, 0.4 times 0.2, which we already did right here. So that is 0.08. And for part E, it asks you to calculate the expected value and the standard deviation. So the expected value is basically the mean of a proportion problem, which is NP. So I'm using everything from that chart that I just made. So it's going to be NP, and then I'm going to add all of them together. So this is just a 0 times this plus 1 times this plus 2 times this, which equals 0.66. And then for standard deviation, this is a hefty one. So it is all of the square root, and then we're going to take n minus mean, or expected value squared, and then times it by the probability. So we're going to do this for each one in the column 0, 1, and 2. And then add them all together, and you get 0.62. Okay, and finally now for the AP question. So the AP question says, investigators at the U.S. Department of Agriculture wished to compare methods of determining the level of E. coli bacteria contained in beef. In beef. 2 different methods, A and B, of determining the level of contamination were used on each of 10 randomly selected specimens of a certain type of beef. The data obtained in millimicrobes per liter of ground beef for each of the methods are shown in the table below. And here is the table, just a visual. And then it asks us, is there a significant difference in the mean amount of E. coli bacteria detected by the two methods for this type of beef? Provide a statistical justification to support your answer. Okay, so for our first part of phantoms, I identified the parameter as the level of E. coli bacterial contamination in beef, and the null hypothesis and the alternative hypothesis as the mean difference equals 0 and the mean difference doesn't equal 0. And the mean difference is the mu of A minus the mu of B. That is given to us in our chart. And so we can assume independence. We can also assume normality due to the histogram. Because n is only 10 observations, we would proceed with caution, but I also graphed it. So the histogram is relatively symmetrical, so this displays normality. And here's the histogram. I just did list 1 and list 2 of the observations we were given, and then did list 3 as list 1 minus list 2, and graphed it. Okay, so continuing with phantoms, our n is name the test, and this would be a matched pairs t-test, which is t equals the mean difference minus 0 divided by the standard deviation of the difference divided by the n value of the difference. So I obtained our degrees of freedom, which is 10 minus 1 equals 9. And then I'm going to use the alpha level of 0.05. And then for my test, I carried it out and I got my t value of 1.46. So then I went in my book, in my chart, and found that p is between 0.10 and 0.05. And that was only in the book, and then I plugged this equation into the calculator and I got the p-value of 0.1793. So according to my alpha level of 0.05, my p-value is greater than my alpha. So that means we fail to reject the null hypothesis that the mean difference is equal to 0 due to the significant level of 0.05. So for our statement, we say that we fail to reject the null hypothesis that the mean difference in the two methods A and B of determining the level of contamination of E. coli bacteria is equal to 0 due to our p-value of 0.1793 being greater than our alpha level of 0.05, thus not proving that our null hypothesis is incorrect. We also do not have enough statistical evidence to conclude there is a difference in the mean amount of E. coli in this type of beef.